Here we go, welcome back. Here we got series rules for the DC circuits. We got 3 rules, we got 1 equation. Actually we have 2 equations, but 1 equation for now, and at the end I'll tell you the other equation to find power. Okay, first rule says equivalent resistance is additive. That means resistance 1 plus resistor 2 plus resistance 3, etc. equals R total, or equivalent resistance. Okay, so in this circuit down here, we have a series circuit because there is a single wire that attaches all resistors and the battery. Okay, and we have a 3 ohm resistor and a 3 ohm resistor. Now we know right here, because of the way the plus here and the minus here, the big side of that is the positive and the small side is the negative. We know that conventional flow says it goes this way. But we know in actuality that electrons don't really happen that way. Electrons is what's flowing and it really goes that way. But we're going to learn conventional flow, which says this. So that is resistor 1. That is resistor 2. Okay? So as a given from the first rule, we know that my first resistor has 3 ohms of resistance. The second resistor has 3 ohms of resistance. So that means 3 plus 3 has an equivalent resistance of 6 in a series circuit. Okay? The next one says the current is the same throughout. So that means any part of the wire in this circuit is going to have the same current. The current is calculated using Ohm's law, I equals V over R. Now, in order to understand that, we know that we have a total voltage from our battery, which does not mean that there's only 6 volts. It doesn't say 6 to 0. It could be 250 volts and 244 volts. And the difference is 6 volts. Okay? So the potential difference that makes this happen is going to be 6 volts. So we know the total voltage is 6. So in order for us to find the current, which the current is the same throughout, I'm going to have to use this equation, I equals V over R, which says that the totals, 6 ohms of resistance and 6 volts of potential difference. So it's going to be 6 over 6 gives me 1 amp of current. 1 amp of current. Okay? Now, since the rule says current's the same throughout, I have 1 amp that goes through that one, 1 amp that goes through that one. So I can actually figure this out pretty simple. Now, in order to work backwards, if I want to see the voltage drop across each one of these, I can use this equation rearranged, which is V equals I times R. Okay? And we know this is our third rule that I'm kind of overstepping a little bit, but third rule says voltage drops proportionally across each resistor, ends with no volts. Okay? So that means it's going to drop half of it here and half of it here since they're the same size. Now, resistor 1 has a voltage drop, and you would show this in a diagram of a voltage meter. It would look like that. The difference of this side and this side, something happens inside that resistor that says, it could be a light bulb, it could be your radio, it could be anything, but it drops a certain amount of volts. Okay? So we're going to use this equation. 1 times 3 is 3 volts. A potential difference for voltage drop. Okay? Now, since this is the same size, we know it's going to be the same right there. And total voltage, 3 plus 3 gives me 6. My series rule says 1 plus 1 plus 1. I'm sorry, not 1 plus 1 plus 1, but current is the same throughout. Resistance is additive, so 3 plus 3 is 6. Now, your power is voltage times current, V times I. So I really don't even need to look at this anymore. If I have these first 3 pieces right, I can just look at V times I. Power equals voltage times current, which is going to give me 3 watts.